Hello everyone, this is Professor Chen, Mechanical Engineering. Today I'm going to give you a 5-minute head up for Chapter 6. And this is our fourth and also the last loading. We call it transverse loading. And transverse loading usually occurred also in a beam model. However, in these situations, we not only consider pure bending, but we consider is an arbitrary loading conditions. So for example, here we have the distributed loading. We have point loading at anywhere you name it. So this is F1, this is F2, and this could be omega as a function of X. So that is a very general situation of the loading. And for this case, let me put the model here. Again, this is a beam model. Upon these situations, you pretty much can build up the loading to draw the bending moment diagram. So for example, here, let me schematically draw the bending moment diagram. For example, this could be something like this, and this may not be accurate, but let me just arbitrarily do it. Okay, something like this one here. So from here you can see, for example, let me designate a portion here. So say here and here. So I take the free body diagram of this portion. So let me highlight here. So that is a free body diagram here. And this is the section size we pick it up. So from here you can see clearly. For example, this corresponding is at point A, this is the point B, and corresponding is point B here, point A here. So you can see the bending at the point A and B is not equal. Because the bending at the two sides is not equal, so for example here, let me say the bending at A, bending at B, here they are not equal. Apparently this is the MB is greater than MA. So from the one homework problem in the chapter 4, I designate you has been able to calculate. And for example here for MB, the stress will be something like this. And MA, the stress here is 0, so basically MA is 0, so basically has no stress. So from there, this is model you should be able to calculate is this. So for example, from here, let me further identify these cross sections. Okay, so here the 3-dimensional view of this free body diagram will be like this. So from the one homework problem in the previous chapter, chapter 4, you have calculated the equivalent force on this cross section here, And you can calculate that is, let me call it FB, and another equivalent force on this section for this example is equal to 0. So that means in terms of the situation, we can look at this model here. Consider this is a beam and under different type of the loading, and once we bend it, and here this free body diagram, this slab basically represented by this. Okay, so here you clearly see this is the portion in the beam. And why we bothered this cross section, because from here right now, remember this one taken away from the whole entire beam. And this is a model here. You can see this force equal to that big, and here is that small. So to keep everything in static equilibrium, which is the underlying assumptions in the whole class here, to make the whole things balanced, you have to imagine is this. This is a beam A, that much, and that is a force that's small. So we must, at the bottom line here, to have the shear force to exist there to make things balanced. So under this model, you can see we must at its bottom side, there must exist certain magnitude of the horizontal force we call H. and H basically is equal to FB minus FA, and FA here is equal to 0. Okay, so due to the existence of this force H, that is induced reactions in the beam, and this will only happen in the beam under this kind of the unevenly distributed point loading. If this beam, again, back to the chapter 4, is on the pure bending, which means the bending on this side and this side are equal, you can deduce this one should be equal to 0. So again, this comes to the very important concept. For transverse loading of the general type like this, we expect the shear stress or shear force on this on each slab there. Okay, and so from here we recognize everything. Then we can begin to do little calculations. So let me say these have the distance delta x. Okay, so that is the distance x, and let me call the width here is t. So the width of that section is t. So basically here with this information, this area, basically the bottom area equal to t times delta x. So we have area, we have the shear force. We simply divide the shear force by the area called t delta x, and that one we say that is the shear stress here. Okay. So that is the formula. So from here, we expect if the beam is under this kind of the general transverse loading, we expect they should have shear stress at each level of the slab, which doesn't exist in chapter 4 under pure bending. And that, again, I want to reinforce this concept during your learning. And from your learning, I think in the first 2 lecture hours, you're going to learn how to derive this one. Basically, this is VQ over IT. V is the corresponding transverse force on this section. So again, and let me pick out this model one more time, not to mess up this drawing. So here, this is the free body diagram, and this is point A, this point B. Okay, so from there, you should be able to calculate corresponding reaction bending and corresponding reaction shear. And how to get these 2 values basically is learning from chapter 5. We learn how to draw the shear and bending moment diagram. You can easily get the numbers. That is a V you use in this equation. And Q is a particular number, and that is the major focus you must pay attention to about the Q. Okay, we will spend 1 to 2 lecture hours how to explain the Q. And Q, that is the major things you're going to learn, and actually it imposes the most challenging part for most students and based upon my past experience. So you have to pay attention how to determine the Q in these chapters. So once we have this one, and I is the moment of inertia as the same we calculated in chapter 4. Again, I is the moment of inertia as the we calculated in chapter 4. And T is the width of the cut. Again, this is the beam, and T is the cut dimension from here to here. Okay. This is the only equation we're going to apply and learn in chapter 6. So in principle, it's simple, but in reality, it's not. And most challenging, again, you have to pay attention to how to correctly determine the Q. And so under these situations, in our practice, we're going to apply the beam of different cross-section. And again, the section can be regular rectangular cross-section, and the section can be trapezoidal cross-sections. And even the section we consider could be like this shape, or we consider is the section is hollow. Basically here we call the box beam. So here that is the many types of the beams under this loading, and then we're going to on this each sections to practice how to utilize this equation. This chapter is long and usually take about 2 weeks, about 6 to 7 lecture hours to learn to go through the whole things one more time, and your learning goal should be pay attention on determine the Q, and then how to utilize this equation to different cross sections. Okay, thank you.